Okay, so now how to create the pulses for the IGBTs. We concentrate on the upper ones here. We create pulses and shifted 120 each one between each one of them. And after that, we take the first pulse or pulses and we complement them. Okay, and we send them to the one in the bottom sides. We do this just to avoid to have a short circuit between plus for this battery and the negative side of this battery here. Okay, we just use my pen to explain more. Okay. So once we generate a pulses for this, let's say for example something like this. Okay, keep in mind that duty cycle it's variable because it depends. It's not constant. We don't compare this this carrier waveform to a constant, but you compare that one to sine wave. That's why you know the pulses sometimes they are smaller, sometimes they are larger. Okay, look here, it's a small pulse negative or yeah, negative here also, and positive here. So positive will be larger than or smaller, sorry, than this part here, and so on. Okay, once you compare, and those are the pulses, and the width of those pulses depends on the intersection between the sine wave and the carrier. And the sine wave, we call it for this one the reference voltage. I'll be talking about this after. So let's say, for example, we created those pulses here for IGBT1. In order to avoid a short circuit here, because these two, they are connected in the same leg and they connect positive side and negative side. So we have to alternate. Okay? To alternate, you have to do something like this. And so on. Sorry. It is 0 should be 1. 1 would be 0, 0, 1, and so on like that. Okay, here we have 1. This one should be 0. This would be on, this IGBT. And in the same time, the other one should be off. Okay, and so on. Once we open, once we close this, close means we make it non-conducting. Okay, we conduct this one, make it on, and so on, like that. In practice, we have to create what we call a dead band. Dead band. Okay, where we have, for example, the first one here. See, the first one here should be like this, just example. So the other one, it was 1 here before. So this is 0, this is 1. Okay, let's say, for example, this one is 0. It's not conducting, but this one was conducting at this time, 1. So we have to make this one 0 before we make the other one 1. So here we have to make this one 0. Okay, so this time here, both of them, they are 0, if you can see this part. And this is what we call dead band in practice. In theory, it's not an issue, but practically we have to use in our controller, we have to specify this dead band here. Okay, we give like depends. Okay, we can give you know a few milli or microseconds. Okay, before we make the other one on. Okay, because practically also this one from 0 to 1 doesn't go sharp like that, but it takes time to reach 1 and so on, like this. Okay, so the other one also, we have to specify this decaying parts here. We have to give that time to this one here before we switch the other one on. So that one will be, we make say we'll give him a time to discharge, let's say, okay, to this part here, and after that, we'll be sure that this one is off, closed, I mean, not conducting. That time you can make the other one on, and so on. So this part here is very critical and very important in practice in order just to avoid making plus or positive side for this DC battery. With the other one, we make them together, connected together. And this is what you call a sharp short circuit for this battery. So to avoid that, we have to take care of this deadband. Now, once we create a process for this one, okay, we make the same shifted 120 for the other one, the next one. How we can do that? With the other reference, with the other sine wave, shifted 120. Once we shift the second reference, 120, compared with the same carrier, this will give us another pulses, and they are shifted 120 to the first ones. And those created new ones, we make a complementary one to them. So let's say, just to be more clear here, say for example, for this one, we have created the pulses to this. The other one, we take the same pulses and we invert them before to send them to this number 6 here, this IGBT. So this inverter makes that complementary signal to that one. Okay, now this one or this one here, the first ones shifted the minus 120 or plus 240, the other sine wave, okay, and those signals will be sent to 5, and the complementary will be sent to 2 here. So we have just to take care about creating the 2 pulse generators, 3 pulse generators, sorry, for those 3 IGBTs, and make complementary for each one of them, and the job is it's done. So here we'll be getting the references with the frequency given to those references here. The reference can be 1 here, okay? Compared to this carrier, and carrier it's 1 also, -1 to 1. Why -1? Because we have a negative sequence for our sine waves and positive sequence. So we need to compare the upper ones, the upper sequences to 1, and the lower sequences here to -1. That's why you have to create a carrier signal. If you remember that repeating sequence, you remember we created that one with, for example, in terms of time, it was 0, and 1/2 times the t here, and 1/t. Okay, and we had 0, 1, and 0 for this DC to DC converter. But for our case, since we need to create a negative part, so those zeros here should be replaced by -1, 1, and -1. This is how we can create this carrier waveform, this triangular waveform with my -1 and +1 as amplitudes. Okay. Now, once you create your references, those signals, the blue and the green and the orange one here, as I can see, it should be the magnitudes depends on the modulation index we need. We call this one modulation index. Okay, modulation index should be all the time, okay, smaller than 1. Okay, because look at this figure here. Okay, below 1, okay, I mean this SPWM works, in modulation technique, and once we cross this one, we make it more than 1, like you can see here. Okay, between this point and this point, okay, we go to what we call over modulation index, because if you have our signal, triangular waveform, and you compare that one with signal bigger than that triangular waveform, the comparison will be here. But here will be, there's no, it cannot compare. The microcontroller will find this one bigger than that one, so it will give either 1 all the time till this one comes smaller than the triangular waveform, or 0 till this comes to, so 0 or 1, it depends. Here, if you can see here, for example, this is bigger than the triangular waveform, we have 1. So if it's bigger, it will be all the time 1. Okay. Till this one comes smaller than the triangular waveform. At that time, it will continue comparing. And okay, till it will get also this one and the other side smaller, so it will be 0 and so on like that. So this, once you do it, like you see your oscilloscope and you get your pulses, okay, with this big, say, duty cycle, means you have overmodulation somewhere. What you have to do, you have just to go to your reference signal and minimize its amplitude, keep it under 1, just to keep yourself in this region here. Okay. Now, there is one thing. This is our exercise today, and we're giving you the VN. This is the battery. This is VDC, 300 volts DC. This is the modulation index. So this represents the magnitude of your references, 0.8. Here, this is the wanted or needed frequency at the outputs. So we need 50 hertz. If we need 50 hertz, we have to create our references with 50 hertz frequency. If we need the output frequency, depends, for example, if we have a motors to be controlled and we need 100 hertz, 200, any other type or any other number of frequency. So it will be our frequency for that reference. Okay, that's the fundamental here, which represents the reference. If we need 100, so this will be 100 hertz. And the references, each one of them will be 100 hertz and shifted 120 degree between each other. Now, how we can calculate the frequency of this triangular waveform? And okay, the frequency of that triangular waveform, which is that, if you remember here, let's say I mentioned here 1 over T, that frequency here. This is 1 over F. I think you are not with me and you cannot correct me. Huh? This is 1 over F. This is 1 over 2F. Because this is time. This is seconds, and seconds. So now to create that frequency or to find that frequency, it depends on this modulation frequency here, MF. So MF, which is the frequency of the carrier divided by the frequency of the fundamental of reference, let's say ref. So our reference, we need our reference to have 50 hertz. So the frequency of the carrier to give to this carrier here, this triangular waveform, will be equal MF times the F reference. So, and this will be, let's say, switching frequency, we call it. So switching frequency will be 40 times 50 hertz, and that's 2 kilohertz. So this is the switching frequency to be given to this triangular waveform, and compared with the references with, it was an example. So our references will be 50 hertz, each one of them. Okay, and after that, once we compare that triangular waveform, sorry, this is the carrier. compare that one to 3 sine waves. And those sine waves, this is the reference. This is 120 minus 120 degree. The amplitude of each one of them will be 0.8 according to this modulation index here, or modulation amplitude. 0.8 each one of them. Okay, so here you can use the oscilloscope here for 2 of them, just to be sure that you created the 3-phase system with the needed amplitude and the needed frequency. Frequency should be specified here, 50 Hertz for each one of them. Okay, so these ones, okay, will be compared to, this is comparator here, to this carrier here. So 3 comparators with the same carrier, and so on. Okay, like that. So these will create, pulses. Same thing for the last one. We create pulses. Those pulses will be sent to this is the upper IGBT, IGBT1. This will be IGBT3, and this will be IGBT5. If you go back to our circuit, it will be 1, 1, 3, and 5. We have 4, 6, and 2. So here, complementary of those signals, like that, will be sent to 4 and 6 and 2. This is 1, that's 3, and this is 5. 8, 3, and 6, 5 and 2, 1 and 4, and they have direct signal with inverted one, direct signal, inverted one, and so on. And those signals, this one and this one, they are shifted 120. This one and the last one here, minus 20 degrees. Okay, so you are requested to simulate that circuit. You have the input. Okay, that's the reference. As I told you, from this one you can calculate your frequency, switching frequency. That's the amplitude, and this is your this is the load, RL load. Okay, so calculate the switching frequency, which is we have done it. That's 2 kilohertz. Plot the waveforms of triangular signal. So this with one reference, you can take one reference, for example. Okay, we need just to have something similar to that one here, this figure here, with only one signal, the blue one, and triangular waveform. You are requested also to generate pulses for switch IGBT1 generated. So we have to plot those pulses for the first one. Okay, you can add here, for example, the complementary one also. So for IGBT1 and IGBT4. Okay, both of them. So we can see like we have pulses and complementary pulses here for this B, question number B. 3-phase line voltage across RL, the output, you should generate the 3-phase line to line. Okay, but I think you have to use something here, like a filter, because if you plot directly here, the signals here, they will not be a sine wave exactly like that, but here we have the sine wave, the fundamental, plus the harmonics created by this switching frequency. Okay, so we'll get something pulses like that. Okay, and so on. Okay, those pulses, they have the fundamental one plus the frequency. So we have to add the filter. I'll let you investigate on this part here. You have to add the filter first order, for example, and just to filter, keep here only the fundamental one, and you can get your three-phase signal after that. So you can plot before and after the filter, and you can compare them. Okay, now discuss the effect of the amplitude modulation index. Yeah, I want you to change it from 0.8 to 1.20 and check in what will happen. Okay, I needed to investigate also on this part and discuss what is the effect of modulation index on your output signals. Do you have any questions? I think I covered everything. And also you got this in the lecture with the professional, explanation from Professor Lazar. Okay, one more time, the frequency for the reference depends on your wanted frequency at the output. If I want here a frequency, I need to generate from this DC here, generate sine waves with the, let's say, for example, 150 hertz, just example. So these should have 150 hertz, the carrier, the references here. We have a three-phase inverter, so three signals, three sine waves with the same frequency, shifted 120. And the frequency of the triangular waveform depends on modulation frequency, the MF. Okay, this you can select it by yourself, or can be given to you. Usually, like I think more than 40 is okay, like that, 40 and so on and more. Okay. Any questions?